Okay. This relation is later on important if you are dealing with a chemical process which deal with compressible gases. Right? Later on you are working with Petronas gas or with Petronas utilities or in British petroleum gas, which you need to control. You need to measure the flow rate of the natural gas. Right? If you need to do that, you cannot use the normal Venturi meter. Because gas is compressible matters, substance. So you need to use this nozzle. Okay? So if you use it, you can calculate the maximum flow rate is fixed. You can change it by changing the stagnation pressure and temperature at the inlet of the fluid. So if you want to change the flow rate of the gas flow in certain pipeline, you can change the pressure of your tank. This is the export tank, this is the import tank. Alright? So you can control it by that. Okay, which means you can accordingly put how big is your compressor need to be installed if you want to deliver certain amount of gas. Okay, so that's the importance of fluid mechanics in pipeline. Okay. Now coming back to here, the mass flow rate reach maximum when PB equal to P star. So what happens if PB is lesser than P star? Does not affect. It will not affect the flow rate because it's already reached the critical condition. Even though you push it further, the exit pressure will be equal to the critical pressure. See that? So even though your PB now is 0, your PB is 0, your PE in here, okay, in this condition, in this location, your PE will be equal to P star. Doesn't matter. Even though you make the PB 0, the exit pressure will still be P star. Remember that. P star is the minimum pressure you can achieve at the outlet of a converging nozzle. Yeah? Which means the maximum flow rate also will not be changed, even though you make it smaller. That's why in this condition, it is stated that the flow is that. Pronounce it yourself. I'm a bit worried with this word. Right? Yes. Pronounce it. Okay? So, in this condition, the flow is maximum. You cannot increase it further. Right? It's stuck there. Clear? So, this is that condition. Okay? And if you look at this table, it's just simply showing you the PB over P naught. When PB is equal to P naught, right? When PB is equal to P naught, when it is 1, of course there is no flow. Okay? If the pressure is the same, there is no flow. When you reduce the PB, then you will start to have the flow. The flow will be maximum when your PB is equal to P star. That is the maximum. When you decrease it further, no changes. Reach maximum, that's it. Right? Your coursework, you got 50. Your final exam, you got 50. That's maximum. Even you cry in front of me, you want 105, I cannot give you. Right? It doesn't really matter for you also, right? So you have reached the limit, that's it. 100 maybe is, like this. You already got 85. Right? You already got 85. That's the maximum. I mean, you will got A, doesn't matter what. Then you just beg me, oh, sir, I want 93. I mean, at the end of the day, you still got A, right? A is the maximum. So, Now, if you look at the exit pressure, which is the pressure at the outlet of the nozzle, you can see when the PB is equal to P naught, right? So your exit is equal to P naught. That's why you got 1. When the PB is equal to P star, your exit pressure is P star. When you decrease the PB, doesn't matter. P star will remain the same. That's how you look at it. Okay, so if you want to change the mass flow rate, the only thing you can change is you change the P naught or you change the area. You make it smaller, you make the mass flow rate smaller. You make it bigger, you make the mass flow rate bigger. So if you have a flow stuck or choked, then you make it smaller. You are not improving the velocity, but you're decreasing the mass flow rate. That's the only thing, right? If you make it bigger, then you get a higher flow rate. Right? So what you can do is either you increase the pressure stagnation, or you decrease the temperature. So in this case, if you want to increase the flow rate in this nozzle, you increase the P naught or decrease the T naught. Make it cooler. You provide a cooler for this. Right? Cooling jacket, make it cooler, then you get a higher flow rate. Okay, any question? No? Okay, I do not want to make confusion to you, but there is sometime we want to calculate the parameters in terms of a critical condition parameters, right? When you have something like this, when you want to calculate mass number here, you are using C over here. When you are using this KRT, you are using T in this location. Now, what happens if we are using T in this location, in the throat, right? This is your throat. So we use T throat to calculate the Mach number in this location. That is those Mach number star. So Mach number star is the Mach number for velocity at that location divided by the speed of sound at the throat. Okay. So it is not MAC but MAC star. So that's the only difference. Okay. Sometimes it is used, but it's not as widely used as the normal Mach number. Okay. So this Mach star is the local velocity non-dimensionless with respect to the sounding velocity at the throat. So you use the condition at the throat to calculate the C, and then your Mach number is V in this location divided by C in the throat location. Okay.